We are about to start. Okay, well, good morning for everyone that is on YouTube. We are about to start. Just a minute or so. Okay, well, Héctor, I'm gonna do a short introduction and then I will pass you the floor, okay? All right, so let's start. Hello everyone and welcome to another talk in our webinar series. Today we have the pleasure of having Héctor Gil-Marín from the Universitat de Barcelona in Spain. Héctor has been a member of the BOSS and eBOSS collaboration and is currently a member of the DESI collaboration. His research focuses mainly on cosmology and more precisely on the large-scale structure of the universe. And today he will talk about cosmology from galaxy redshift surveys, the current results, and the future techniques. Before we start, a quick reminder. This webinar is also being streamed live on YouTube. You can find the link on our website or you can access it on our YouTube channel, LIneA MCTI. Héctor, thank you very much for being with us today. The floor is yours.
Thank you very much. Let me start by sharing the screen. So hopefully you all can see it.
Yes, it's okay.
Thank you. So without any more wait, I will start. So there are essentially, so my talk is about cosmology and the large scale structure of the universe. And I will be essentially presenting BOSS and eBOSS recent results. And also I will talk about some new techniques we are developing for the ongoing DESI survey. So let me start by reviewing the current observational probes we have in cosmology. So essentially there are like two probes. One is the CMB and the other is the large scale structure of the universe. So both of them have some similarities, but they are quite different as well. So on one hand, CMB represents like a two-dimensional surface at very early epoch, and the large scale structure represents essentially a 3D volume at a later time. So in general, CMB it's easier to be modeled because it happens at the epoch where things are just more linear and not that much complicated. On the other hand, large scale structure, first of all, suffers of the effect of dark energy, which is when it enters into play at later times. But it also contains like a lot of information about non-linear physics, which makes it a bit more difficult to model and extract information. And it also contains effects that it can be a bit annoying, such as galaxy bias, peculiar velocities, that when it comes to measure cosmology, you have to like marginalize over them. And if you don't understand them, they could end up causing systematics. So spectroscopic surveys are those surveys that they observe galaxies, or more specifically, more generally, dark matter traces, usually galaxies, but they also can observe intergalactic gas. And they are essentially measuring two things. They are measuring angles of objects and their redshifts. So redshifts are usually converted to distances, and with that you form a 3D map that it's your starting point for extracting information. However, in order to convert redshift into distances, you essentially need to assume two things. You need to assume a certain cosmological model, and you also need to assume that the recession velocities of these objects or of these galaxies are essentially due entirely to the Hubble flow. So this is the outline of the talk, or like a diagram that tells you how cosmology is extracted from this starting point, this large-scale structure, 3D galaxy maps. So on the first stage, there is a compression of this map into what they are called summary statistics. I'm just going to explain very briefly in a bit what these are, but for the a bit experts, these are essentially power spectrum and correlation functions. So from this, the second step is to identify certain robust features into these summary statistics that for the experts, these are essentially the baryonic acoustic oscillation and redshift space distortions. And these are later on interpreted within a certain cosmological model. And these tell us about cosmology parameters such as dark energy, how is gravity at these scales, and also about early time physics such as inflation. So the first thing is this compression into summary statistics. And we have to be reminded that these galaxy maps are essentially non-deterministic. It means that any theory model is not going to describe us how these galaxy maps are going to be in terms of we have a galaxy here or we have a galaxy there. But this needs to be done in a statistical point of view. So we need to essentially expand these galaxy maps and describe them through statistical quantities, which are the so-called correlation functions. So the first one is the two-point correlation function, or the Fourier counterpart, which is called the power spectrum, which essentially is constructed by measuring how many pairs of galaxies we have at certain distances. So the more, as we change the distance of interest, then we count galaxy pairs at these distances, and then we essentially see how they cluster with respect to a random distribution. Because of these maps are non-Gaussian, they contain information from gravity, which induces a very strong non-Gaussianities. The full description of these maps, it cannot be done at the level of two-point statistics or power spectrum. It needs higher order functions to full description. And these are like what they are called higher order statistics. The next leading order is the three-point correlation function, or the bispectrum in Fourier space, which instead of looking at pairs of galaxies, it looks at triangular configurations. And even at higher order statistics, we have the four-point statistics, or the trispectrum in Fourier space, which looks at these quadruplets. So the more higher order you go, then the more difficult it is to extract this information. So you need an estimator which is very efficient to measure this in a reasonable amount of time, but also the complexity of the model, it increases. So for this talk, and I would say it's like the state of art right now, the extraction of cosmology in these maps focused only on this first statistics, which is the two-point statistics or the power spectrum. And this is what I'm just going to be focusing on this talk. So when we come to identify features in this summary statistics, one of them is the BEO, and this is the standard ruler. So what's the BEO? The BEO is the baryonic acoustic oscillations, and it's a phenomena which it happens at very early stages of the universe, when the universe is a plasma with photons and baryons all together coupled. So this coupling generates oscillations, and these oscillations generates essentially pressure waves or sound waves that travels across the universe. So they travel during a certain amount of time until the universe is cool enough that this plasma gets decoupled. And the distance that these peaks travel, they mark this feature, which is like the sound horizon scale. And this is essentially what BO is. It's a distance that these sound waves have traveled during a certain amount of time. So this obviously leaves an imprint in the spectra of photons from CMB that has been measured by many CMB experiments, such as WMAP or Planck. But it also essentially leaves an imprint in the matter distribution of the universe as well, because it's an oscillation of photons and baryons. So when galaxy forms in later times, at the peaks of this baryon density, the distribution of galaxy keeps a remnant from these baryonic acoustic oscillations. So the trick here is that we can use these baryonic acoustic oscillations as a standard ruler to calibrate our measurements. And this is one of the cleanest proofs in cosmology to measure parameters. So there are like two types of baryonic acoustic oscillations analysis. One that requires the absolute knowledge of this horizon scale at the recombination time, which is the time where the baryons and photons get decoupled. And we are going to be referring to this distance as air drag or sun horizon scale. But also even not knowing this scale, by measuring the BO along and across the line of sight and imposing that the BO essentially is an isotropic structure, we also can extract information. And this is what usually is referred as an uncalibrated BO. So as I was saying, how we extract information from this map. So first of all, we assume the cosmological principle, which tells us that the universe is isotropic and homogeneous. And if we remember what I've said at the beginning of this talk, when we transform redshift into distances, we need to assume a certain cosmology model. So if this cosmology model that we assume, it's not exactly the true cosmology model, there are like small deviations, we are going to essentially introduce a fake anisotropy in our maps. So by knowing that the map has to be isotrope, and by measuring the amount of anisotropy we have induced, then we can determine how wrong this assumed cosmology model it is. So this is what it's described in this talk, in these pictures. So this wrong cosmology model distorts radial distances. It distorts all radial distances, but in particular, it distorts BO distance, that is a distance that we can measure very well. It distorts it obviously radially because it's a conversion between redshift and radial distances, but also it touches the distance at what angular clustering there is. So essentially it modifies two distances. It modifies the BO distance along the line of sight, but also modify the BO distance across the line of sight. And these two distances are what they are called DH and DM. They are all functions of this H parameter, which is the Hubble expansion, which describes the expansion history of the universe. But if you see here, the radial BO distance is essentially a measurement of this H at the redshift of the galaxy map, whereas the angular distance is the whole integrated effect of this Hubble parameter between redshift 0, so today, and the redshift of our map. So essentially, using BO scale, we can, an Alko-Paczynski effect with them, we can play and infer things about the universe and in particular the amount of matter. So let me remind you that at recombination time, so when there is this decoupling between photons and baryons, then the BO peak essentially has this size, which is the sun horizon scale, which is a quantity which depends on the components of the universe and the physics of the universe before recombination. But then when this peak is imprinted in the distribution of matter, and in the end in the distribution of galaxies, because of the expansion, when we are measuring the BO, we are not measuring the sun horizon scale, but we are measuring the sun horizon scale times the expansion history of the universe at the time of the galaxies of that map. So essentially, the BO analysis tell us about this H time drag, which is what is usually referred as the isotropic dilation of the BEO. But you can also look at these two distances along and across the line of sight, and then we can take the ratio of them. So we can cancel out this dependence on the absolute size of the BEO. And by just looking at the ratio, we essentially can measure the amount of matter, which is like, this is actually what is called the Alko-Paczynski effect, whereas this is not Alko-Paczynski, this is just an isotropic dilation because of the expansion. So just the takeaway message is that from BEO, we have essentially two measurements. One is omega matter, the amount of matter in the universe, from this ratio of distances by imposing that the BEO has to be an isotropic structure. And the other thing we can measure is h times the horizon scale that comes from the absolute size of the BEO at a certain time. There is another source of anisotropy, apart from induced by the Alko-Paczynski, which is like what is called the Redshift space distortion. So again, remember that we assume that the universe follows this cosmological principle that is isotropic and homogeneous. And again, there are another source of anisotropy that we can measure, that it comes when converting galaxies, redshift into distances. So if you remember what I've said today before, we need to, in order to construct the map, we need to assume a certain cosmological model, which is what I just mentioned before. But we also need to assume that the recession velocity of the galaxies are entirely due to the Hubble flow. But this is actually not entirely true. There is a main component of the recession velocity of galaxies, which is due to the Hubble flow, yes. But there is another component, which is called peculiar velocities, which arises from the fact that the galaxies interact with each other, interact with the nearby galaxies, and they tend to attract each other. So these peculiar velocities actually contaminate this distance to redshift to distance translation, and they actually end up putting galaxies in wrong places by this component. So this, in principle, annoying thing is actually very useful because we can actually model. So the peculiar velocities of the galaxies essentially depends on two physical parameters. It depends on the amount of matter in the universe. So the more matter there is in the universe, the more galaxies there are, and therefore the more attract to each other. And also it depends on the theory of gravity. If theory of gravity is different than GR, then this attraction force can be weaker or stronger, and therefore we will end up observing a higher or lower peculiar velocity component. So this is translated into this function, which is called f, or the logarithmic growth of the structure of the universe, and essentially it arises from this parallel to the line of sight component of the peculiar velocity. And it's going to be a parameter that we can put in our model and just measure by looking at how anisotropic this structure is. Just to have a visual idea of what the redshift space distortion look like, on the right in blue, there is like an isotropic distribution of galaxies. And in the left in green, there is these same galaxies, but with the position shifted because of these redshift space distortions. And then you see essentially that it produces a squashing in the direction perpendicular to the line of sight, but also creates an elongating features along the line of sight at small scales, which for those who are familiar, these are called fingers of God. So when it comes to model all this, the modeling itself, it can be quite complex, but just to give you an idea, let me present like just the linear component of more complex models, which is just the Kaiser toy model. We don't use this model to really analyze data from galaxies because it's too simplistic, but it really helps to give an insight on what's going on. So essentially, the Kaiser model relates the matter power spectrum of the underlying dark matter field with the galaxy power spectrum in redshift space. So the first thing is that there is an additional component which is called mu, which is the angle between the cosinus of the angle between the pair and the line of sight. So there is here a description that we have our telescope with a certain line of sight among two pairs of galaxies. So the angle that makes between this line of sight on the median of the pair and the vector between the two galaxies, this is mu, this is beta, sorry, and the cosinus of beta is what we call mu. So if this pair of galaxies is totally perpendicular to the line of sight, we have that the cosinus of 90 degrees is 0, so mu is 0, and we don't observe redshift space distortion, essentially because we are just looking at pairs which are perpendicular to the line of sight, so we don't apply any distortions. And in this case, the power spectrum of these pairs of galaxies is just the bias, the galaxy bias, times the matter power spectrum. But as long as this pair forms a certain angle with this line of sight, then there is this mu component which arises, and it reaches the maximum when the pair is totally parallel to the line of sight. And then it has this F parameter, which is the growth of the structure of the universe, which is sensitive to it. So essentially by measuring, one could think that we can bin in K, but we can bin as well in mu, and then we can measure F by essentially looking at how the clustering changes as a function of mu. However, we can, in practice, it's more useful to do another thing, which is expand this pk mu function in terms of Legendre polynomials. And the first Legendre polynomial, the amplitude of the first Legendre polynomial, the composition is what is called the monopole. And then the second is the quadrupole, and the third is the hexadecapole. There are no dipole or octupole signals, essentially because this dependence is mu squared. So the the odd functions of this Legendre polynomial essentially cancel out with the even functions of this functional form. So we can work out and translate this Kaiser model into the form of this monopole, quadrupole, and hexadecapole, and they can be written in this way. So we see here that by measuring this and by assuming a certain shape for this matter power spectrum, by actually measuring the different amplitude of these functionals, then we can get information on these colored things, which essentially we have two unknowns, which is the bias and the growth factor, F. So essentially by at least measuring two, we can break the degeneracy and extract information on this B and F. There is something additionally that is an extra unknown parameter, which is the absolute amplitude of the matter power spectrum, which usually it's parameterized as a sigma 8. So this cannot be broken at the level of this Kaiser model. So instead of measuring B or F, what we measure with what we are sensitive to is F times sigma 8 and B times sigma 8. So B times sigma 8 is not used usually in cosmology because B is not a cosmology model, it's more a galaxy formation thing. So we are not interested as much in this, but the relevant quantity is this so-called F times sigma 8 or directly F sigma 8, that is what people usually talk about. So coming and having like a summary of what I have explained so far. So we have this observed galaxy maps that we compressed in this summary statistics or 2-point correlation function and power spectrum for this work. And from them, there are essentially three quantities that they are relevant, which is like the BO distances along and across the line of sight, and this F sigma 8 thing, which is sensitive as well to omega matter and gamma. So these are usually called a compressed set of parameters because essentially we compress at a given redshift. We compress all these summary statistics in just 3 numbers. And using these 3 numbers at different redshift bins, then we can assume a cosmology model and then extract information in terms of cosmology, gravity, inflation, etc. So here it comes to the application of all these formalism that I just explained. And the benchmark for application are spectroscopic surveys, and the larger or the state of the art in terms of spectroscopic surveys are BOS and EBOS. So these are essentially a spectroscopic survey. We have been observing galaxies for 20 years, from the beginning of the year 2000 until last year. And it traces like a very large volume from redshift of around 0.07 up to redshift 0.3 by 3.5 by observing different type of galaxies. So from nearby galaxies at redshift below 0.2, then luminous red galaxies, LRGs, at intermediate redshifts. And then at higher redshift, we have the emission line galaxies, or the ELGs. And even at higher redshift, we have quasars. And even at higher redshift, where there are almost no galaxies to be observed, we have this so-called Lyman alpha, which is emission lines from the intergalactic medium, which are illuminated by background quasars. So these also can be used as a dark matter tracer, and we can play the BEO and RST. So BOS and eBOS essentially have two patches. One is the Northern Galactic Cap, and the other is the Southern Galactic Cap. The Northern is a bit larger because of the position of the BOS telescope. It's in New Mexico. So during the whole year, it has more access to the Northern Galactic Cap, but it also can map a bit of the Southern Galactic Cap, although it's smaller. So this is like there was the BOS collaboration in numbers, but there are like also the BOS, the personal BOS part, or the eBOS part, which is like the all people that for these 20 years have been working very hard to put up these maps as to be accessible for everyone and can be used. So it's not as simple as just observing the galaxies and making the maps. There are a lot of intermediate work that all these people have been doing for the last 20 years. So these are like the final product of the BOS and eBOS. So this is like essentially the map. So if you want to see an animation of the map, you can click on here. I will pass the slides afterwards, but I'm not going to reproduce it here because it's just this image, but moving through. So from this map, from this image, we can essentially see two things. We see the North Galactic Cap here, the South Galactic Cap here. We see also the obscure regions, which are because of the plane of our own galaxy. And as we look at to larger distances, we also look back in time, and the closer galaxies, we have this bright galaxy sample, which are nearby galaxies. And then as we go farther and farther, we see the LRGs, and then the ELGs, and the quasars, and finally the Lyman alpha. And in all of these samples, we can play this game and identify BEO and RSD. And by the identification where this peak position, then we can trace back where the cosmology information interpretation comes. So all the BOS final papers came out during summer, Northern Hemisphere summer last year, July 17th. And they were like a coordinated submission of 20 papers, and essentially doing this BEO and RSD analysis on the different samples, but also the description on the catalogs, on synthetic catalogs that they were used to estimate the errors, and also the description of the catalogs, of the true catalogs of the data themselves, and some other statistics analysis. So, so to summary, on each of these tracers, so they are listed here, we have essentially identified these three compressed variables, the BEO and F sigma H. This comes by measuring these three expansion on the power spectrum, which are like the monopole, the quadrupole, and the hexadecapole. So by measuring these, we have compressed into these three statistical variables, as I said, the BEO and F sigma 8, which represents measurements at different redshifts. So here I'm just showing how it looks in terms of F sigma 8 normalized by the F sigma 8 predicted by Planck, and how each of these galaxy maps at different distances put essentially a measurement with a certain error bars, and then we can fit different models to them and extract information. So I'm just going to briefly explain what are the main conclusions from the BOSS and EBOS survey. So the first one is dark energy. So before BOSS, we had the detection of dark energy from the supernovae. And also we had Planck data from CMB, which was also sensitive to dark energy through the BEO. But now there is a third and independent measurement of dark energy, which comes from the BEO measurements, the uncalibrated BEO measurements at these different samples, which is shown in this plot in blue. So this plot shows the amount of matter in the universe listed as omega matter, and in the y-axis, the dark energy listed as omega lambda. So why BEO does so good in measuring omega lambda, or at least with respect to this other? So the unfair advantage that BEO has with respect to these two is that it uses measurements at different redshifts. So essentially Planck uses just one single measurement at very long distance at redshift 2000. Pantheon supernovae, it's essentially at very low redshifts, but BEO really feels what is in the middle. And by looking at how the BEO changes as a function of time, this is really sensitive to dark energy. And this is essentially the unfair advantage of BEO with respect to the other two. So apart from this detection of dark energy at many sigmas, so dark energy is at many sigmas non-zero, not only by supernovae or Planck, but also by BEO. What is interesting to see is how good the BEO also can say about whether the universe is flat or not. So the flatness of the universe essentially is described by this dashed line, which makes this sum of omega lambda plus omega matter 1. So you see that the intersection between these different probes is essentially around here. So it coincides with the universe being flat. So these are two of the main conclusions in terms of lambda CDM from BOSS and EBOS. We can also look at deviations from the standard lambda CDM model, which is we parameterize the dark energy not just as a constant, would be W0, but also like a time evolving function, very simple, parameterized by this free parameter WA. So we try to measure whether WA is 0, whether W naught is different or not from -1. So here they are showing the constraints coming by adding Planck data to Pantheon supernovae. They are shown in red, and also by Planck data plus SDSS. So we see that essentially the blue and the red contours are very complementary, are very orthogonal. So on one hand, SDSS is very good at measuring curvature or omega k, and we see that the constraints on this parameter are very good, but it's not very good at measuring W. We see that there is a white contour, oh, here better, there is a white contour on this parameter. However, when combining blue and red, these are two orthogonal proofs, and then we have this gray contour, which actually measures pretty good omega k and omega 0 at certain time, and also omega a, this time evolving parameter. So the result is that omega a is very consistent with 0, so a non-time evolving dark energy, although the error bars are still large. And as I've said before, the conclusion is that the universe is very close to be flat. Omega k is 0, and this other parameter omega 0, it's very close to -1. That's the corresponding for dark energy coming from vacuum energy. There's another interesting thing in terms of cosmology, which is what does BEO has to say about the famous H0 tension. So for those who don't know, there is a parameter in lambda CDM, which is H0, which is the expansion of the universe today. And there are essentially a group of experiments, essentially led by Planck, which wants a value of this H0 parameter around 67. And there are all other set of parameters essentially led by supernovae observation at much later time, where once a value of around 73, 74. And these two values are now at many statistical sigma, so they cannot be explained just as a fluctuation. We know that has something wrong, either in the lambda CDM model or in the way the supernovas are calibrated. So if you remember, the BEO actually does not measure by itself H0. It measures H0 times the horizon scale, R3 or R track. And then these are represented by this light blue line here, which is this band, which represents a constraint on H0 times RP. So, however, BEO can be combined with data coming from BBN, or Big Bang nucleosynthesis, which essentially uses abundances of hydrogen and helium in the universe to determine the information on how many variants in the universe there are. And by knowing how many variants in the universe we have and knowing the physics between the end of inflation and the time of the coupling, we essentially can calculate this distance of the sound wave traveling through the plasma made of photons and baryons. So by doing this, we can make we can infer our drag and combine BEO with air drag. And this ends up with an H0 of around 68, which is in very good agreement with CMB measurements by Planck, which are represented here in gray. We can take also these BEO measurements, and instead of using the BBM, we can combine them with CMB analysis from Planck and also add information from the supernovas, but without calibrating supernovas. So, and also allowing for a very general model of the universe. So it's an open lambda CDM with time evolving dark energy. And we see that even adding uncalibrated information from the supernovas, the value of H0, it does not move much. It stays of around 68. And so again, this is in tension with what is called the supernovas, which are around 74. And what we can do with BEO is, instead of using the uncalibrated supernovas, use the calibrated supernovas to actually anchor the BEO measurements at H0 of 74. And this is shown in this purple contour here. And what this does is, instead of being in tension on H0, we have forced the BEO H0 to be the one that supernovas wants. So now, instead of having an H0 tension, what we would have is a tension of RD. So essentially, BEO can be fit either with a high or low value of H0, depending on whether you think that what is wrong is the calibration of the supernovas, then it would have like an H0 value around here. Or if you think that there is something wrong with the physics of the sun horizon scale at a very early times, like early dark energy, then what it would be wrong is to interpret BEO by BBN using this function here. And then what it would be right would be to have a higher value of H0. But just to, just to be clear, BEO, it does not measure by itself H0, and it's consistent, strictly speaking, with both of them. So finally, BOS and EBOS also are sensitive to neutrinos, and in particular to the sum of the neutrinos. So there are essentially two theories for the neutrinos. One is to have 3 species of neutrinos, but one with low mass and 2 very massive. And the other is the opposite, is to have 2 very massive and 1 light. These are like these 2 hierarchies, like the normal hierarchy and the inverted hierarchy. And essentially for these 2 hierarchies, there are like a limit in the higher mass of the sum of the neutrinos. One is like at 60 MeV, and the other is at 100 MeV. So in this plot, what we are showing is like the constraints from combining the BEO information from SDSS or BOS and EBOS with Planck, and also adding RSD information and also adding supernovae in these different colors. So we see that from Planck in red, Planck is not very sensitive and it cannot distinguish between this limit. But as long as we add information in terms of BEO, we have the green, and if we add RSD information as well, then it comes to the blue. So there is a slight preference from the normal hierarchy, because if we interpret these posteriors as Gaussians, then this limit of the inverted hierarchy is at 2 sigma. But we have to bear in mind that the maximum of the posterior, so like if we fit a Gaussian posterior to the actual posterior, it lies in an unphysical region of negative masses for the neutrinos. So this is essentially telling us that our error bars are still too large to have this maximum in another place, like close to here, which is like more likely to be. And therefore, the interpretation of this 2 sigma, it's a bit hand wavy in the sense that it's 2 sigma, but then we need to say that the most preference mass for the neutrinos, it lies in an unphysical region. So this was the end of the first part of the talk that was describing the state-of-the-art measurements in terms of cosmology. And in the second part, I will briefly describe DESI and a few projects that I'm working on. So DESI, it's a next generation spectroscopic instrument. It's the natural continuation of BOS and EBOS. It has started observing at the beginning of this year, and it will last for the next 5 years. It will observe 1/3 of the sky, or what is the same, like 40,000 square degrees. And as BOS and EBOS, it will use different traces from braid galaxies to LRGs, ELGs, quasars, and also Lyman alpha forest. And it will essentially cover the same redshift bin. It will the same redshift range. It will be cover more area, and it will be more dense. So the main target of DESI is to measure BEO, RSD, as well as mass of the neutrinos and FNL, which are primordial non-Gaussianities. And the first results from the first year of observation, which will cover 1/5 of the total volume, or 3,000 square degrees. It will probably come out by the end of next year. So what's new about DESI? It's like the instrument. It has this amazing technology of robotic fibers. So this is an image of the focal plane of the telescope, where each of these, it's formed by 10 petals. In this image, you can see one of the petals. And in each of one of the petals, they are holes where these robotic positioners are placed. So these robotic positioners are essentially fibers, which essentially takes the light, and through this stick, the light travels and it goes into electronics, and it goes to the spectroscopy, where you essentially break the light into different colors, and then you identify spectra. And what is new is that this robotic positioner, they actually move a bit in order to lie on the exact precision of the position of the galaxy for each new area of the sky. So in total, there are like 5,000 among the whole focal plane, and this is an image actually from observing Andromeda, and how the different fibers are collecting light from not only Andromeda, but also different galaxies around the field. So it also, as you can see, the field of observation is huge, because Andromeda, it's a very large object in the sky, and it can actually be captured by the whole focal plane. So there are like some forecasts made in terms of the background expansion history, or this parameter h, and also the growth of the structure. So in the colors here are some of the measurements from BOSS, and the gray represents the forecasted error that it will be estimated from DESI, in gray using galaxies, and in black using Lyman alpha at higher redshift, and as well as the same thing from the growth of the structure. So because of this large area of DESI, the error bars are forecasted to be quite small, and essentially it's going to detect potential deviations from the prediction of this lambda CDM model. So just to finalize my talk, I'm just going to present two projects that I have been involved within DESI. The one thing is blinding. So far, all the experiments in spectroscopic surveys hasn't been blind, but there's like this tendency in science, both in particle physics, but also on cosmology, to start making blind analysis. And why this is done, this is essentially wants to avoid confirmation bias. Essentially, we want to avoid looking for bugs in our pipeline until we retrieve what we want from data. Essentially, we want to decouple the search from bugs from the pipeline to what data is telling us about the universe. So the key thing from this spectroscopic survey DESI, it's BEO and RSD. So we aim to do two types of blinding. One is blinding for BEO, and the other is blinding for RSD. So in order to blind for BEO, what we need to apply is an Alko-Paczynski type of geometrical distortions along the line of sight. And from RSD, what we need to do is a distortion along the line of sight, but proportional to the perturbation. So it's going to essentially blind the growth of the structure. So the idea is to modify the positions of the galaxies that we are going to observe in order to imprint a fake signal in such a way that what we measure from the data, we know it's not the truth. So we can actually use the data to test other stuff, but not based on the true cosmology of the underlying data. So as I said, because the added value of a spectroscopic survey is not the position of the galaxy, but its redshift, its angular position. These blindings are not going to be in terms of just moving the positions of the galaxies, but we are only going to be modifying the radial direction of the galaxies. So in this first type of this geometrical Alko-Paczynski fit, it consists of essentially assuming some arbitrary cosmology, as we've done so far, to convert redshift into distances. But then in the intermediate place, then we are going to go back and convert distances into what they call blinded redshifts using what they are called shift cosmology, that in principle it's not known. And from this blinded redshift, then we can apply again this arbitrary fiducial cosmology, which is known in principle to get blinded distances. So by doing this, what we are imprinting is a shift on the BEO parameters, the retrieve DH and DM BEO distances. And this shift is proportional not only to the shifted cosmology that we have chosen, and in principle it's secret, but also to the fiducial cosmology that we have arbitrarily chosen. There is another type of blinding that it's not on the background, and it's not an Alko-Paczynski type of blinding, but it relies on the growth of a structure. So what we want to do is to use a technique called reconstruction, which essentially remove all the signals coming from redshift space distortions. And in principle, it does this only at linear level in perturbation theory, but at least at large scales, it will work. So we can remove these redshift space distortions induced, and we can actually reapply them using a different factor. So essentially, we assume a fiducial factor for the growth of the structure. We remove redshift space distortion based on this theory and by this assumption of this factor. And then we reapply a new set of redshift space distortion by a new factor f prime, that is our blind cosmology. So we have actually tested how this works in this paper here. So we have done an analysis on these BEO parameters. They call alpha parallel and perpendicular, but in reality they are DH and DM. So we have analyzed our blinded catalog in red and the original catalog as well in blue. And actually we have also corrected the analysis on the blinded catalog by this factor here. So we know that the original alpha and the original alpha prime, which is the blinded, they are related by this quantity. So once the cosmology, the blinded cosmology, the circuit cosmology is revealed, is known, we can actually shift the analysis on the blinded catalog, and then we see that it actually matches very well the analysis that we could have done in the original catalog. And this is not only done on BEO type of analysis, but also on what they are called full shape or RSD type of analysis, where we are not only blinding these alphas or DH and DM distances, but also F sigma 8. And again, we see that it works, this technique works very well, and it's ready to be applied to any spectroscopic survey, but in particular to DESI. If I have time, I also want to present another work that it has been done for DESI, and essentially is to extend this standard analysis based on these compressed variables, DH and DM and F sigma 8, to something else. So there is further information in the shape of the measured power spectra, which is beyond the BEO position and beyond the RSD function, the RSD, the redshift space distortions, which is actually the shape of the power spectrum, which is sensitive to parameters such as omega matter, omega baryon, H, AS, etc. So there are recently in the literature, they have appeared some type of analysis that we are referring as a full modeling analysis that essentially skip these intermediate variables and directly fit the full shape of the power spectrum and fit the variables of the model they are assuming. So they've claimed that there are more information beyond the BEO and RSD that you should be extracting, but then the question is where this information comes from was not clear. Also, whether this information is robust under potential systematics, etc. So just to give you an idea, I remind you this like the standard approach that we had. So from the maps, we were doing this summary statistics, this power spectrum correlation function. We were extracting these intermediate galaxies, and from these intermediate galaxies, we were inferring cosmology. So what this full modeling analysis proposed is actually to skip these intermediate galaxies and directly assume some cosmology model and directly fit the summary statistics without caring about this intermediate stuff. So what's best and what's worse on these two approaches? So in principle, the standard approach is more model independent because it needs to assume a cosmology model, but it does at very final stages of the analysis. So after these compressed variables are measured. It relies on late time physics, whereas the full modeling, it's more early time physics. It generates Boltzmann code linear power spectrum. So this is early time physics. And from that, it imprints late time physics, but it imprints it afterwards. It does not use any type of compression, whereas the standard way, they compressed all these summary statistics in just 3 parameters. So I would say that the standard approach, it relies more on what it can be observed from actual data, whereas this full modeling approach, it relies more on what theory tells you about this data. So if we compare in terms of the amount of information that these models retrieve, so in gray, we have this standard way of RSD, and in orange, just combining RSD with BEO. So if we plot these constraints in this parameter space on this lambda CDM assumed model, we see that the constraints on the gray and the orange are much more wider than what the full modeling has to say, which is like this blue line. So it looks like the full modeling is extracting more information than from the standard RSD, but where this information comes from, it was not very clear. What it was clear though, it is that when this large-scale structure information is combined with CMB, Planck, the amount of information is the same. So Planck, when adding Planck data, doing this full modeling, it actually not adds anything more. Or in other words, Planck saturates the amount of information that it's come from either one or the other analysis. And actually, what Planck measures, it's the transfer function of the data of the power spectrum. So this actually tells us a bit of what's going on here. So we proposed in this paper this extension on the compressed set of variables, and instead of working with these BO distances and F sigma 8, we also add another parameter, which is called M, which actually regulates the actual tilt of the power spectrum at large scales. So in principle, we propose this functional form in terms of 2 free parameters. So this M1 would be sensitive if interpreted within lambda CDM on the combination of omega matter times H. And this second parameter, it would be proportional to NS. But because of these 2 parameters are very degenerate, what we have done so far is to fix NS or M2 to some fiducial value and just play with one extra free parameter, which is this M1 that we are going to essentially refer as M. So M is actually this tilt. So as we change M, this tilt changes. And we see that actually the calculation, the variation on these cosmological parameters such as omega matter, omega baryon, and NS are very well captured by varying this M parameter. So these are just the takeaway message from this extended version. So from standard BO, the compressed variables, they are working in terms of DH and DM. And if we translate them in terms of lambda CDM variables, they are sensitive to omega matter and to H time the sun horizon scale. By adding redshift space distortion analysis, we add this extra parameter F times sigma 8. But because of lambda CDM variables, F is tied to omega matter through gamma, which is fixed by GR. What we actually measure within lambda CDM is sigma 8, which is essentially a measurement of AS. And by adding this extra parameter that this methodology that we call shapefit it's called M, it's a measurement essentially of omega matter times H. So now, if we work in terms of this extended set of compressed variables, and then we compare with this full modeling, what we get is the following. So actually we get very similar constraints, just working in terms of compressed variables or directly doing the shape fit. And this is essentially what is shown in this plot, where the green contours are coming from shape fit and the blue are coming from full modeling. And you see that they are very close to each other. So just as a summary, BOS and eBOS is today the sample with largest redshift range than any other proofs. And it has demonstrated percentage level precision on measuring BO distance scales at different redshifts. It also have provided growth measurements at redshift below 0.5. And all these have been in good agreement with lambda CDM and Planck results. And they have performed a detection of dark energy using BO only data. So on the other hand, DESI has just started observing. So by the end of next year, it will deliver the first year results. And it's as agreed that the DESI analysis has to be blind in terms of BO and RSD, because the results are going to be more robust. And we have presented a methodology that it's allow for this blinding. And also, we have shown that there is extra physics beyond the BO and RSD, and this relies essentially on the transfer function. And this extra information might be used from DESI to extract extra information in terms of cosmology parameters. So if you want to do this, you don't really need to do full shape type of analysis that essentially requires you to assume a certain cosmology model from the beginning. But you can use this shape fit methodology, compress variables, just as a natural extension on the current state of the art method, that it retrieves essentially the same information as the full model. And this is all. I finish here, and sorry for the extra time I have been using.
Thank you, Héctor, for the remarkably interesting talk. We now have time for questions from the audience. If you joined us on YouTube, you can put your question in the comment section, and I will redirect it to Héctor. And if you joined us here on Zoom, you can raise your hand and ask your question yourself. So questions? Okay, that's well. While we wait for questions, I'm actually got interested. How long are the integrations for the DES experiment? Because you have a lot of fibers and faint sources that you want to observe. How does that work? Are you coadding information?
I know. I mean, I'm not an expert, first of all, but I know the observations usually take around 20 minutes. But it really re-observes the same area several times. So I know that for BOSS and eBOSS, the same galaxies were observed between 3 and 4 times, I think. So each area needed like 4 or 3 times 20 minutes observation. So it's around 1 hour and 1 hour and something. And I assume that for DESI, it's going to be similar. DESI has more fibers, so it can observe essentially 5 times more galaxies in each of these 20 minutes observations. But in order you need to essentially get the spectra with enough precision that allows you to determine the redshift with an error which don't affect your cosmological measurements. And this essentially can be calculated, and they have determined that the observation time needs to be around a total time of around 1 hour.
Okay. What values of magnitude are we talking about of these sources? What is the limiting magnitude?
I don't know. I don't know. I mean, it depends on the object, but I mean, usually ELGs are I think they are the most faint objects. Quasars are quite bright and usually they can be confused with stars of the field. But I think the ELGs are the most faint object, but I really don't know what's the actual value in terms of magnitude.
Okay. Also, maybe for someone that it's a little bit a layman on cosmology, there is this difference measured by Planck and other experiments. Is there today any candidate for explaining these differences?
Right. So you mean the H-naught tension?
Yeah,
right?
at the H-naught.
Yes.
Yeah.
So I mean, there are essentially 2 explanations. One is that, I mean, most of the let's put it. So the experiments that measured the low value of H-naught, which is around 67, they usually rely on early time universe. Whereas the experiments that measured higher H-naught, which are around 74, they rely on late time universe, which is essentially the supernova. So it was thought at the beginning that it could be something in the early time that actually makes this measurement wrong. And this is essentially early dark energy. So if you have early dark energy, your measurements from Planck are correct. It's just you are interpreting them in a wrong way. Essentially, you are assigning a value for the sound horizon scale, which is wrong because you are ignoring the effect of early dark energy could have in this early time physics. I am not aware of any model that allow you to modify the expansion history of the universe at late time that can make you explain this high value of H0 observed by supernovae. However, what it can explain the value of the high value of H0 by supernovae is if you are calibrating supernovae in a wrong way. So this is essentially if there are several populations of supernovae with different physics and you are ignoring this, you are essentially treating them as if all of them were equal. And it has been many times in the past, starting by Hubble with the Cepheids. And we know that astrophysics is complicated. So they rely on calibrating things that they don't understand very well. So they could essentially getting a wrong value of H0 by using a wrong calibration. And these are like the two main explanations. Either there is something in the early universe, like some sort of dark energy component, but this to me seems a bit of ad hoc value. So we modified the theory using this now another type of dark energy just to make lambda CDL model fit in this parameter that is not exactly fitting. So I don't like it very much. And I particularly, and this is a very personal opinion, I think it's more likely to be some problem with the calibration of the supernovae.
Yeah, that makes a lot of sense. Well, thank you. Let's see if there is another question. Okay. Well, if there are no more questions, we will now wrap this up. This presentation will be available on our website and on LIneA's YouTube page. And for the next week's webinar, we will start our LSST broker series with Thomas Mathewson from the NOAO, and he will give us an overview about Antares, the astronomical time domain event broker. Thank you everyone for attending, and a special thanks to Héctor. Thank you, Héctor, for taking your time to give us this amazing talk.
Thank you very much for inviting me.
And everyone have a great day, stay safe, and I hope to see you all again next week.